In this module, we look at correlation. Quite often in research, we are interested in the possibility that two variables might be correlated or related in some way. It may be that one causes the other, or it may be that they are related because some other variable is somehow tied to both of our variables. For now, we'll just deal with the calculations and a few of the assumptions behind it. We are going to be dealing with something called Pearson's R, or the Pearson Product Moment Correlation Coefficient, but Pearson's R for short. Now, Pearson's R is about the simplest kind of relationship that you might imagine. Things can be related in lots of different ways, and we, in this introductory course, deal only with linear relationships. That is, when two variables are related in kind of a straight line fashion. Now, what do we mean by straight line, or what do we mean by any pattern, really? We need to take a look at a scatter plot to get an idea about the different kinds of relationships that could exist. If we had two sets of scores, we'll just call them X's and Y's, and we somehow suspect that they could be correlated, what we really should do is use graphing software or get SPSS to do this, but you can do it by hand. Is really just take each pair of numbers and use those numbers as coordinates to plot a point on a graph. We call it a scatter plot. The first point would be an X of 4 and a Y of 10. We would find 4 along the X-axis, 10 along the Y-axis, and we would plot that point here. And we'd plot a point for every one of these pairs of values. Now, I'm not going to plot these particular ones because I want to show you some different patterns. What if you plotted a bunch of points? Assuming you have fairly large samples, you're going to get some a pretty fair number of points to plot. And your points distributed themselves in what's a fairly obvious pattern. In other words, it's not just a random kind of pattern we're getting with all these points, but it is a fairly complex pattern, not linear. Well, if we saw a scatter plot like that, we would not jump to the conclusion that we should compute Pearson's R to tell us just how strong that relationship is, because Pearson's R assumes that when we get our scatter plot, we're going to get some kind of a pattern that would be very nicely fit by a straight line. Now, that is a very nice fit. It could be that the relationship would be linear, but that it wouldn't be that strong a relationship, in which case we would have a lot of points that didn't actually get very close to that straight line. But the point is, if it looks like it's a straight line kind of relationship rather than some other more complex kind of relationship, then it's okay to compute Pearson's R. Like many statistical formulas, there are a couple of possible ones. There's kind of a definitional formula. R is equal to the sum of all the zx times zy values divided by n. Now, that would take a lot of work. It's a nice, simple-looking formula, but what we'd have to do is we would have to turn each of these x values into a z-score, using the mean of the x's and the standard deviation of the x's to do it. And then we'd have to turn all the y values into z-scores, using the mean of the y's and the standard deviation of the y's to do that. So we would now have two columns, one zx, one zy, and then what we would do is multiply the first value in each column together to get the zx1, zy1 product, and then for the second, zx2 times zy2. And once we had all those products, we'd add them all up and we'd divide by n. A lot of work. It's not the way we're actually going to do it, but that's the definitional formula. Now, that can take on values anywhere from a -1 to a +1. You can get a Pearson's R of anywhere from -1 to +1. Negative 1 is the highest possible relationship you can get, as is positive 1. You can't get a relationship higher than 1, either positive or negative. 0 represents no relationship. Some value between 0 and either positive 1 or negative 1 indicates stronger relationships. So as you go from 0 either toward positive 1 or toward negative 1, you're talking about stronger relationships. What's the difference between positive and negative? Well, if our function, when plotted, looks like this, we're talking about a positive relationship. On the other hand, if our function were to look like this in some way, we'd be talking about a negative relationship. And you can see what that means. A positive relationship is one where low, that's interesting, I switched x and y. Low x values would be accompanied by low y values. High x values would be accompanied by high y values. That's a positive correlation. Negative is just the opposite. With a negative correlation, low x values are matched up with high y values, or high x values are matched up with low y values. So when we do our calculations, we better come up with something between negative 1 and positive 1. Now the formula we're actually going to use looks like this. It's a computational formula. It is one of several computational formulas that are around. By the way, we do use lowercase r. Uppercase R stands for something else, so don't make this a capital R. Here's our formula. The numerator may be new to you, but the denominator has two terms that are very familiar by now. The sum of squares of the x values and the sum of squares of the y values. Just computed the way we have done it right along. So we're going to have to use the x's and the y's to get a sum of squared x and then a sum of squared y. Find the product and then take the square root of that. That's what is in our denominator. The numerator is called the sum of cross products. I'm going to teach you the formula for sum of cross products by pointing out to you that it's almost like taking the sum of squares formulas for x and y and sort of pushing them together so they become kind of a hybrid formula. Now that sounds a little scary. What I'm going to do is show you that the sum of cross products is very much like the sum of squares formula. And I'll do that over here. Here's our raw score formula for the sum of squares of x's. Here's our raw score formula for the sum of squares of y's. Whoops. And here is our formula for the sum of cross products. Now notice up here, the first term of this formula is basically summing up all the x times x's. And for the y's, it was summing up all the y times y's. Well, the sum of cross products, the first term, this is sort of like combining the two formulas now, is the sum of all x times y's. Right? Instead of x times x and adding all those up, y times y adding all those up, we get x times y, and we add all those up. So we're going to need a column of those cross products, all the x times y's. I'll just do one of them for now just to show you what we're going to be doing. 4 times 10 and then we'll get the product of all the others and we'll add them up. The second term, up here, notice that we take the sum of all the x's and multiply it by the sum of all the x's. For the sum of squares for y's, we get the sum of all the y's, multiply it by the sum of all the y's. Down here, we're going to get the sum of all the x's, and we're going to multiply it by the sum of all the y's. Once again, it's like combining those two formulas, and it is going to be over n. So, two sum of squares formulas and one sum of cross products formula that looks very much like the combination of those two. All right, so we've got a little bit of work to do. First of all, getting the sum of squares of the x's. I've done some of these calculations. In fact, I've done just about all of these calculations ahead of time. Here's what we get for the x's. For the sum of all the x's, we get 25, and if we take all the x squares, we get 145. If we take the sum of all the y's, we get 70, and if we take the sum of all the y's squared, we get 1020. So we'll deal with those first. Sum of squares of x's, that's going to be the sum of all the x's squared, that's 145, minus the quantity, the sum of all the x's, the quantity squared, that's 25 squared over 5. 145 minus 625 over 5, that comes out to be 145 minus 125, which comes out to be 20. So over here, I've got one of my denominator terms. Sum of squares of x's is 20. Now I'm going to compute the sum of squares of y's. So what I just put up, I'm getting ready to erase. Sum of squares for the y's. Well, that's going to be the sum of all the y's squared is the first term. That was 1020. Minus the sum of all the y's, the quantity squared. That would be 70 squared over 5. 70 squared is over 5 is 980. And so our sum of squares for the y's is 40. Second term in our denominator is done. And now for the sum of the cross products. Well, we have to finish out all of these cross products. So down here, 2 times 14 is 28. 8 times 18, I don't know that, but I've done it. It's 144. 5 times 16 is 80. And 6 times 12 is 72. If we add those together, we get 364. So let's do the sum of cross products. Sum of all xy's, 364. And then all we have to do is use these two totals that we've already gotten. We need the sum of all the x's times the sum of all the y's. That's going to be 25 times 70 divided by 5. So 25 times 70 is 1750 over 5. That's 364 minus 350. And that's 14. numerator is 14. 14 divided by the square root of 20 times 40. If you multiply 20 times 40 and take the square root of that, you get 28.28. If you now divide that into 14, you get 0.495. 0.495, a rather modest correlation, but still some degree of relationship. That's a good bit higher than 0, not near as high as 1.0, but a fair relationship. That might be something that has an impact on how we feel about some theory, a theory that says that there should be a certain correlation between X and Y perhaps, or maybe it's a practical concern we have. Maybe we have some test score, we're calling the X's, and we hope to use that test score to predict some kind of later performance, a Y measure. A correlation of 0.495 would give us a little bit of an ability to predict Y scores if we knew the X scores ahead of time. But that's it for the calculations.